Miss. In this video, I'm going to talk about logical operations and truth tables. Enjoy! Please subscribe, click the bell, like, share, and put your comments below. Let us define that hot means 70 degrees Celsius or more. Suppose that we have two cups A and B. Cup A is filled with boiled water. Cup B is filled with water from the tap. We measure the temperature of the water in those two cups. The water in cup A is 95 degrees Celsius. The water in cup B is 20 degrees Celsius. Then the sentence, the water in cup A is hot, is a proposition with value true. And the sentence, the water in cup B is hot, is a proposition with value false. This is an example of logic with two values, in this case true and false. This is a classical logic. It has only two values, true and false, or 1 and 0, or on and off. Now consider the same example again. We measure the temperature of water in cup A again 20 minutes later. It is 60 degrees Celsius. It is not hot, but it is also not cold. It is warm. So we need more values than just two values true and false, or 0 and 1. We need values in between 0 and 1, like 0.5 or 0.7. This is an example of a fuzzy logic. It has not only values 0 and 1, but also values between 0 and 1. Consider again the same example above. When we measure the temperature of the water in cup A for the first time, it is 95 degrees Celsius. So at that time, the sentence, the water in cup A is hot, is a proposition with a value true. 1 hour later, we measure it again. It is 40 degrees Celsius. Then the sentence, the water in cup A is hot, is a proposition with value false now. So it depends on the time. This is an example of a temporal logic. It has two values just like in the classical logic, but with time aspects. Now we are just going to focus on the classical logic and call it simply logic. We are going to use 0 for false and 1 for true. A proposition is a declarative sentence that can be evaluated either true or false, but not both. A primitive proposition is a proposition that cannot be broken down into simpler propositions. Example of a primitive proposition are 1 plus 1 equals to 2. This is John. 2 is a prime number. Examples of non-primitive propositions are, this is not John. 1 plus 1 equals to 2, or 1 plus 1 equals to 3 minus 1. If it is raining, then I am not going to campus. Acclamation or command sentences such as, what a beautiful flower! Get up and take a shower are not propositions. Also, interrogative sentences are not propositions. Is Jakarta the capital city of Indonesia? So, it is not about the answer that matters, but the evaluation of the sentence. A proposition can be symbolized by a letter. We will use lowercase letters to represent propositions. For example, P is the proposition 1 plus 1 equals to 2. Q is the proposition this is John. A truth table is a table that evaluates the values of a proposition for all possible combinations of its primitive components. These are three basic operations in logic. The first one is the negation. It is denoted by this symbol and is read as not. Not P gives the opposite value of P as shown in this truth table. If P is 0, then not P is 1. If P is 1, then not P is 0. The second one is the conjunction. Use this symbol and read as N. P and Q gives only 1 if both values are 1, otherwise zeros as shown in the truth table below. Alternatively, to see this, that P and Q is the minimum of the values of P and Q. The third one is the disjunction. Use the symbol and read as OR. P or Q gives only 0 if both values are 0, otherwise 1 as shown in the truth table below. Alternatively, to see this, that P and Q is the maximum of the values of P and Q. The following are secondary operations. Secondary in the sense that these operations can be done by basic operations. The first one is implication. P implies Q is written like this. There are several ways to read this. If P, then Q. P only if Q. P is sufficient for Q. Q is necessary for P. P implies Q gives only 0 when P is 1 and Q is 0. Otherwise 1 as shown in the truth table below. To remember this, you can associate this as follows. If you don't promise anything, it does not matter you fulfill it or not. It is always okay. So this is when P is 0. It does not matter the values of Q. Now, if you promise something, then it is not good if you do not fulfill it. This is when P is 1 and Q is 0. This is the only 0 for the implication. Of course, it is okay when you promise something and fulfill it. Next is biconditional. We write like this. We say that P if and only if Q. We also use this. We say that P is necessary and sufficient for Q. P if and only if Q gives only 1 when the values of P and Q are the same. Otherwise, 0, as shown in the truth table below. So here, the value is 1 only if the values of P and Q are the same. The hierarchy of these operations are as follows. Not is the top priority, and OR have the same priority under not, then the implication, then the biconditional. This means that when we write like this, P implies Q if and only if, not P or Q and R, then it should be read like this. Suppose that P is the proposition, this is John. Q is the proposition, the girl is Mary. Then, this stands for this is John and the girl is Mary. And this represents this is not John. And this stands for if this is John, then the girl is Mary. Look at these examples. Example 1. Evaluate the proposition P and not P. According to the hierarchy, this should be read like this. This proposition has only one variable, namely P. So there are 2 to the power 1. That is 2 possible values of P, namely 0 and 1. This 2 is for the 2 possible values. This 1 is for the 1 variable P. We put P in the first column. Not P is not a primitive proposition. It is a proposition P with the operation not. Its values are just the opposite of those of P. We put it in the second column. Next, we evaluate the original proposition, P and not P. Look at the truth table for operation N. In this case, Q and Q is substituted by not P. The operation N gives the minimum values of the operands. So we get the values of P and not P are all zeros. Example 2. Evaluate P or not Q. Here there are 2 variables, namely P and Q. There are 2 to the power 2, that is 4 combination values of P and Q. This 2 is for the number of values 0 and 1. This 2 is for the number of variables P and Q. We put the possible combinations systematically like this. There are a total of 4 possible combinations. The first column is for P. The first half of the 4, namely first 2 rows, are zeros, and the second half are ones. The second column is Q. We put alternately 0 and 1 like this, starting with 0. Next, in the third column, we put not Q. This is just the opposite of Q. Now we are ready to evaluate the main proposition P or not Q. So we are going to evaluate OR of the first column P and the third column not Q. Look at values of the first and the third columns, which are both zeros, and put 0 for P or not Q. The rest is 1. Example 3. Evaluate P and Q and R implies P or R. So, there are 3 variables, namely P, Q, and R. Systematically, we set the possible combinations of values like this. The total combination is 2 to the power 3, that is 8. There are 2 possible values for each variable, namely 0 and 1. There are 3 variables. Put P, Q, and R in the first, second, and third columns respectively. In column P, put the first half, that is 4 rows, all zeros, and the second half, all ones. In the column Q, put the first 2 rows, all zeros, the second 2 rows, all ones, the third 2 rows are all zeros, and the last 2 rows, all ones. In the third column, put alternatingly 0 and 1 starting with 0. In this systematic way, you will cover all combinations and will not skip any. The fourth column, we put P and Q. Now look at the column P and the column Q and see the values of both ones. Put ones in those rows in column P and Q and put 0 for other rows of that column. Next, we put P and Q and R in the fifth column. Look at the fourth column and the third column. Similarly, look at the rows where both values are ones. Put ones in those rows of the fifth column and put zeros for other rows of that column. Next, we put P or R in the sixth column. So we consider column P and column R. Look at the rows where both values are zeros. We put zeros in those rows of P or R and put ones for other rows. Finally, we evaluate the main proposition P and Q and R implies P or R. We put it in the seventh column. So, this is the fifth column implies the sixth column. Now look at the rows where the fifth column is 1 and the sixth column is 0. For these rows, put 0 in the seventh column and put ones for all other rows in that column. We see that we get all ones for this proposition. A proposition which values are all ones is called a tautology. Example 4. Evaluate P and open bracket P or Q close bracket if and only if P. There are 2 variables, here P and Q. So here are the combination of values of P and Q. Note the brackets. Evaluate P or Q first. Put this in the third column. This is just like the truth table or before. Next, we evaluate P and open bracket P or Q close bracket. Put it in the fourth column. So, that is the end of the first and the third columns. Look at the rows where both values are ones. Then, put ones for those rows in the fourth column, otherwise zeros. Finally, we evaluate the main proposition in the last fifth column. Look at the first column and the fourth column. If their values are the same, then put ones in the fifth column. We see that we get all ones for this proposition. For by conditional propositions, we use the symbol and say that the left and right propositions are logically equivalent. So the proposition in this example is a tautology. It is called an absorption law. Example 5. Evaluate P implies Q if and only if not P or Q. Following the hierarchy, we have to read this like this. There are two variables and so the combination of values is like this. In the third column, we evaluate P implies Q, which is the same as the truth table of the implication. In the fourth column, we put not P. This is just the opposite of P of the first column. In the fifth column, evaluate not P or Q. We put zeros in the rows, but the fourth and the second columns are zeros, otherwise ones. Finally, we evaluate the main proposition in the last column. We put ones in the rows where the values of third and the fifth columns are the same. We can see that the values of this proposition are all ones. So, this proposition is also a tautology and we write like this. We call this equivalence the Implore law. Implore stands for implication or. In the next video, we will talk about the laws of logic. Example 6. Evaluate P and open bracket P implies Q close bracket implies Q. There are two variables and so the combination of values is like this. In the third column is P implies Q as in a truth table of implication. In the fourth column is P and P implies Q. So we apply that AND strategy to column 1 and 3 and we get these values. Finally, evaluate the main proposition. So that is the fourth column implies the second column. Notice the order. It is not the second column implies the fourth column. We look at the rows which have 1 in the fourth column and 0 in the second column. But we find none of such rows. So all values are ones. So this is a tautology and we put this symbol for this implication.
This is called modus ponens in rules of inference.
We'll focus on this in the next videos. Example 7. Evaluate not open bracket P or not P close bracket. There is only one variable here. So here are the possible values. Then in the second column is not P, which is just the opposite of P. In the third column is P or not P. So that is the OR of the first and second column. This has values all ones. Then finally, the main proposition, which is not of the third column, so the values are all zeros. A proposition which has values all zeros is called a contradiction. Exercises. Now you can try to evaluate the following propositions using truth table.
That's all, guys! Hopefully, you understand these materials. See you in the next video. Bye!